Hello dear students, welcome to Pen and Paper Chemistry on YouTube. We are continuing with this video, the properties of phenols. But before we do that, please don't forget your pen and paper because you are going to take down notes for offline reference. So are we ready? In this video, we shall be talking about the Reimer Tiemmann reaction and we shall also be doing the mechanism of the Reimer Tiemmann reaction. So make sure that you are writing down what you are understanding. What is Reimer Tiemmann reaction? What is the basic purpose of it? Here we introduce a CHO group or what is called as the formyl group at a position ortho to the OH group. So the product that we get is known as salicylaldehyde. Now this is its common name. What will be its IUPAC name? So we are converting phenol to, what is the IUPAC name? Of course our aldehyde group gets preference. So 1, 2. So we have the IUPAC name of this compound as 2-hydroxybenzaldehyde. Are you writing it down? Okay. Now this salicylaldehyde actually has a very pungent odor, smell like almonds, and it is colorless. How do we bring about this change? This is done by using aqueous NaOH and chloroform. Giving us salicylaldehyde. Yes, it's the next higher degree of oxidation was salicylic acid. Correct. That we had done by what method? How had we prepared salicylic acid? Can you recall? Yes, we had done it by the Carbene method, COOH. Right? Introducing the carboxyl group in the phenol molecule. Interestingly, the Reimer Tiemmann reaction can also be used. So we go a step further and we carry out Reimer Tiemmann reaction using again aqueous NaOH. But instead of chloroform, we bring about the reaction with carbon tetrachloride. So we have the next degree of oxidation product, which is OH and a COOH group on the benzene molecule. So what is the product here that we are getting? Very correct. This is salicylic acid or 2-hydroxybenzoic acid. Now that we have written the names of these products, let us go on and understand what is the mechanism of this reaction. Now you must be wondering why I am teaching you mechanism, whereas for the others I have not done that. Simple, it's there in the syllabus, we are supposed to cover it. For ease of explanation, I have already listed it down for you, the steps of the mechanism. I have broken it down so that I find it easier to explain to you. Now, in the mechanism of, when we talk about the mechanism of Reimer Tiemmann reaction, I'm going to break it down into steps. So, first step here is involving phenol and chloroform getting affected by the strong alkali which is there in the reaction mixture. So, what I've done is phenol in the presence of sodium hydroxide getting converted into sodium phenoxide. And chloroform getting converted into dichlorocarbene. Now, it's a lot of information to absorb at this point. So, let's do it step by step. So, our phenol here, we know that phenols are good acidic substances. In the presence of a base, that is NaOH, our phenol gets converted into phenooxide ion. You remember we wrote the reaction gets converted into sodium phenoxide ion. Sodium phenoxide. Now this sodium phenoxide is actually phenoxide ion and sodium ion. What does the phenoxide ion do? Yes, it releases the electrons towards the benzene ring And what did we say? That these electrons are released at the ortho and the para positions. Now my phenoxide ion becomes electron rich. And if it is electron rich, that means it wants somebody who is positive in nature. In other words, it is going to behave as a nucleus loving species or as a nucleophile. Come to chloroform, CHCl3. Now we know that chlorine with respect to carbon is highly electronegative. Under the conditions of the reaction, chlorine pulls the electrons towards itself and hydrogen is left sadly with a positive charge, because carbon, what it is going to do is it is going to pull the electrons from the CH bond, because electrons are being pulled from it by the chlorine, right? Now OH negative shares its electrons with the hydrogen. With the result, we have something as an intermediate where carbon is carrying a negative charge, forming a carbon anion intermediate. Now this carbon anion intermediate obviously will be very unstable. So what we have over here is we've got an equilibrium setup here. Now this CCl3, either it will try to revert to the original state, or if you see, we've got a strong alkali in the reaction mixture, right? Of course, we should not forget the water here. Now because we've got a strong alkali in the reaction mixture, the CCl3 ends up losing the Cl negative ion from this molecule, the carbon anion that has been formed. Our carbon is now left with a lone pair of electrons. Look at the structure of this CCl2. It is bonded to two chlorine atoms and it has got a lone pair of electrons. In other words, how many electrons does this carbon now have? 2 here, 2 here, and 2 here. That means it has 6 electrons in the valence shell. This particular intermediate species is known as a carbene intermediate. You're not going to come across this type of intermediate at the course level that you are doing at present. But yes, this intermediate does exist, wherein carbon has a sextet, that means 6 electrons in its valence shell. And specifically the name of this carbene intermediate is dichlorocarbene intermediate. This dichlorocarbene intermediate is now short of electrons. Short of electrons means it will try to go to some place where there is an excess of electrons. In other words, it itself is going to behave as an electrophile. Next step. Now we have a nucleophile, we have an electrophile. What an ideal combination in the reaction mixture. So immediately our nucleophile attracts the electrophile onto itself and says, see, I can donate electrons to you. Now when it does that, they do form a bond. And because carbon has been given electrons by the benzene ring, it says to the hydrogen, okay, I won't let you go away. I can share my electrons with you, which I have shown with the help of this arrow. So we have the intermediate wherein instead of CCl2, it is reverting to the dichloro state, CHCl2. Next step comes the hydrolysis. So wherein the 2 chlorine are replaced by the OH group. So nucleophilic substitution, hydrolysis. Remember? Now, you know that a carbon bearing 2 OH groups is not very stable. So let's get rid of the water molecule from here. Now when it gets rid of the water molecule, what do we form? Yes, of course, we have CHO group at a position ortho to the OH group, what is known as, we repeat, salicylaldehyde, or please write the IUPAC name, 2-hydroxybenzaldehyde. Now, in your best interest, I think you should write down this mechanism once again. Now that you have understood, why don't you pause this video and try writing this mechanism once again for better clarity. So you have two reactions, two steps here. So 1, 2, then your combination between the electrophile and the nucleophile, giving you an intermediate. Now here comes the rearrangement. That means they arrange between themselves. There is no other external molecule involved. There is rearrangement giving us the intermediate, which on hydrolysis finally gives us salicylaldehyde. That's why pen and paper. Please write it down. In the next video, we shall be completing some of the miscellaneous reactions that I have given in the chart. The coupling reaction, which we've already done under diazonium salts. And of course, our favorite phenolphthalein, which we will be using in the laboratory. How is it prepared using phenol? So stay tuned, stay connected, because we are just on the last leg of this topic.